Hey everyone, I hope you're doing well. My name is Max and I'm a TA for Fundamentals of Computer Systems, and today I'm going to be walking you through a question on digital building blocks, which also involves a little bit of circuit timing and digital logic. So in this question we're given three logical functions f, g, and h with the schematics provided right here. And the first part asks if the three schematics compute the same or different functions. So essentially the easiest way to do this is just to enumerate through all possible inputs of A, B, and C. Because there are only three inputs, we have 2 to the 3 rows in our truth table, and that means that we only have to go through 8 examples, which should hopefully be relatively pain-free. So we have the truth table computed here, and you see that if A, B, and C are equal to 0, and by the way, I do recommend pausing this, working through the truth table yourself just to solidify your understanding of the digital building blocks, and then coming back and watching the video. But if A, B, and C are 0, then F, G, and H will all be 1. If A and B are 0 but C is 1, then F, G, and H will also all be 1. If A is 0, B is 1, and C is 0, F, G, and H all output a 0. If A is 0, B is 1, and C is 1, they also all output a 0. But then if A is 1, B is 0, and C is 1, F and G will output a 1, but H will only output a 0. So because we ran into some combination of A, B, and C, such that the three functions provide a different output, we know that these three functions are not logically equivalent. So they do compute different functions, these three schematics. And if we are to walk through the next two rows, you'll see that one of them is the same, I believe it's the last one, and then these two do provide different values. So the functions are not equivalent. The second part of this problem gives us the schematics again, and also gives us this table with areas and critical paths. And it asks us to compute the areas and critical paths of F, G, and H. Computing the areas is actually pretty straightforward. I don't know if you guys talked about it in class, but you essentially just sum the areas of the individual components. So for F, you would sum the area of a 4 to 1 mux, which is 10, with the area of an inverter, which is 1, so you get 11. For G, you sum the area of a 2 to 1 mux, which is 5, with the area of an inverter plus the area of another inverter, so that gives you 7. And then the area of an XOR gate, which is 4, so you also have an area of 11. And then for H, you sum the area of a 3-input OR gate, which is 3, with 3 2-input AND gates, each of which have an area of 3. So you get, you essentially get, there are 2-input AND gates have an area of 2, so you get 9 from that, because 3 plus 2 plus 2 plus 2 is 9. And then you have two inverters, each of which have an area 1, so you also get 11. Something that's interesting to note is even though these three circuits have the same area, they do compute different logical functions, so that shouldn't necessarily be correlated in your mind, right? It doesn't make sense. Area can't predict what function it computes. Our next task is to compute the critical path of the following functions. And this is essentially just the longest path you can take to get from your inputs to your outputs. So for F, you can go through the inverter and then through the 4 to 1 mux, and that is 0.5 plus 4, so that would be 4.5. For G, that would be going through the XOR gate, then through an inverter, and then through the 2 to 1 mux, so that's 2 plus 0.5 plus 3, so that's actually 5.5. And then for H, the longest path you can take is going through an inverter, then a 2-input AND gate, and then a 3-input OR gate. So going through an inverter is 0.5, through a 2-input AND gate is 1, so 1.5, and then through the 3-input OR gate is 1, so we get 2.5. Again, the areas and the critical paths are not necessarily correlated. The third part of the question asks us to give a function j that computes the same function as f, but has a shorter critical path than f, and it asks for j's schematic, area, and critical path. So our immediate thought here should be that f is not optimized in some way, and what tool do we have kind of in our toolkits for optimizing circuits? Hopefully what comes to mind is K-maps. So we can make a K-map for f using the truth table that we computed in part 1, And the K-map should look like this. And again, I encourage you to pause and work through this part of the problem and then listen to my explanation. But from looking at the K-map, we see that we can kind of group these three terms, or we can make these three groups, and we ultimately get this logic function, which is not A, not B, plus not B, not C, plus ABC. And all we have to do from here is turn this into a schematic. And so my first thought is maybe a 3-input OR gate with an AND for not A and not B, so inverters there, then an AND for not B, not C, so inverters there as well, and then an AND for A, B, C, so that would be a 3-input AND. And that's actually exactly what the solution says. So we have the 3-input OR gate, the two 2-input AND gates connected to the inverters, and then the 3-input AND gate also connected to A, B, and C, C before it hits the inverter. And from here we need to compute the area of this circuit and then the critical path. So the area would just, again, be the sum of the components. So even though a 3-input OR gate looks really big, it actually only has an area of 3. So we add 3 plus 2 plus, we add 3 plus 3 for the 3-input AND gate, plus 2 for the 2-input AND gates. So right now we are at 10 because 3 plus 2 plus 2 plus 2 is equal to 10. And then we have 3 inverters, so we add 3 times 1 to that, and we have a total area of 13. We then need to compute the critical path, and so the slowest path this can actually take, well, we need to compute how long it takes to go through, because there are two kind of possibilities here. One is that it goes through a inverter, and then through an AND gate, and then through an OR gate. The other is that it goes straight through the 3-input AND gate, which could potentially be slower, and then it goes through the OR gate. So the either way, it goes through the 3-input OR gate, which has a delay of 1, so again, it's super fast. If it was just to go through the 3-input AND gate, it would also have a delay of 1, so that would be 2. If it goes through an inverter and a 2-input AND gate, that has a delay of 0.5 plus 1, so that actually takes a little longer because it's 2.5, and essentially that is the overall critical path. It's 2.5. So we now need to see if H has a glitch, and if it does, we need to provide the input transition that triggers it, and if it doesn't, we need to argue why this wouldn't be the case. So we start by making a K-map for H, and again, I encourage you to do that, and this is what we're given. We kind of see that it's perhaps a bit suspicious because there's a little bit of overlap between AC and A naught, B naught, so let's actually test that out. So there are different length paths from A to H that could potentially cause this glitch. One such path is A to the inverter to the 2-input AND gate, and that gives you not A, not B. And the other one is A to the 2-input AND gate, which gives you AC. And on the transition from A equals 1 to 0, so when A is falling, AC will drop to 0 before A naught, B naught rises to 1, and this causes a glitch. So I hope this video is helpful. I hope you guys are getting more comfortable with digital logic and building blocks. These are super helpful, and I hope you are all doing well.
Okay, what's up? So today we are going to implement this truth table using a variety of muxes. And so we're going to start off with the H1 mux. And we're essentially just going to translate from here to an H1 mux. So let's just get started by drawing out our H1 mux. So, got this mux here, and the mux, since it's an 8 to 1, is going to have 3 selector bits. So I'm going to put that here, 3, I'm going to say A, B, and C. Okay, and then we're going to have 8 input bits, so or I guess 8 input lines. So 1, 2, 3, 4, 5, 6, 7, 8. And it's going to be like the 0th input line, 1st, 2nd, 3rd, 4th, 5th, 6th, and 7th. Okay, and so then remember what a mux does. It basically just says depending on the value of these selector bits, it selects one of these input lines, and then it outputs the value on the line. So let's say that ABC was equal to 0, 0, 1, right? So that's my selector bit, like these are my selector bits that I'm feeding into here, and that is basically telling the mux, like, okay, output whatever value is on this input line, because it's the first input line, right? So like, it's the, first input line. Okay, so let's say that, I don't know, we have the value of Q1 here. Okay, so if that is the case, and I'm feeding 0, 0, 1 in as the selector bits, it's going to say, okay, well, output whatever is on the first input line, which in this case is Q, so it's just going to output Q. And so using that, we're essentially just going to use the mux as a lookup table here, right? Since we have 8 input lines, okay, and we can choose any one of those input lines based on a value of the selector bits, which are A, B, and C. And so we're literally just going to like directly translate this truth table onto this mux. So in this case, if ABC, going with this example, were 0, 0, 1, right, what would I want to output? Well, I want to output a 1. Okay, so I'm just going to put a 1 here. Okay, if ABC were 0, 0, 0, I want to output a 0. So I'm going to put a 0 here. Because if I were to feed in 0, 0, 0 into as my selector bits, right, I want whatever is on the 0th input line to be output, which is a 0, so that was that line. And then we're literally just going to translate directly from here to here. So 0, 1, 1, 1, 0, 1, 0, 0. And this is just going to be our out over here. And then we are good. So that is our answer. We're literally just making a lookup table with this 8 to 1 mux from going directly from the truth table to here. Okay, so then for the 4 to 1 mux, this is going to be a smaller mux. With 4 input lines, 1, 2, 3, 4. And we're going to have 2 selector bits. So I'm going to pick A and B. And so what this means is that it's not going to be a lookup table anymore. We're going to have to actually apply some logic here on the left side with the input, with all the input lines, in order to ensure that we get the correct output. So let me just like shrink this down. And so let's check out our truth table. Okay, so AB can either be 0, 0, 0, 1, 1, 0, or 1, 1. So let's start off with the case that AB is 0, 0. We want to then output, the mux, if I feed this 0, 0 as my selector bits, the mux is going to output whatever is on the 0th input line. So looking here, when A and B are both 0, we can see that the output, wait, I'm just looking here, A and B are both 0, we can see that the output is just C, right? So that means that I want to just feed in C here. And so what will happen then is the mux is going to say, like, it's going to get the 0, 0, and it's going to say, great, I got 0, 0, so I'm going to go to my 0th input line, and I'm going to see, well, my 0th input line is attached to C, so just output whatever the value of C is. And so if the value of C is 0, it's going to output 0. If the value of C is 1, it's going to output 1, which is exactly what we want. And then so, proceeding in a similar manner, let's see if A and B are 0 and 1. So if A, B is 0, 1, then we want to output, what do we want to output? We just want to output 1. Because regardless of what C is, it's just going to output 1 either way. So okay, we're just going to feed a 1 into here. And then for our third case, here we go, 1, 0. Let's check out the truth table. So we can see that again, the output is just the exact same as C. So I'm just going to feed C into here. Okay, and then for our last case, when AB is 1, 1, that is going to be these last 2 rows of the truth table. And in that case, we're just going to have 0 regardless of the value of C. So I'm just going to take a 0 and feed it into there. And there is our 4 to 1 mux implementation. Okay, so then the last thing we have to do is the 2 to 1 mux. So let me draw that out over here. 2 to 1. And so this is going to be like a small box, right? We only have one like selector bit. So here's my A, and then I have these 2 input lines. So that means that we're going to need to put more logic here on the left half in order to correctly translate from the truth table to the two-door mux. So we have 0 and 1, and these are our two input lines, and we have our one selector bit to control which of the input lines we want chosen. So I'm going to pick A as my selector bit, and looking at the truth table, I'm going to say, okay, well, I have two possibilities for A, right? Is a bit, it's either 0 or it's 1. So that means that we have two cases here. We have A is 0, we have A is 1. Okay, so when A is 0, I need to output this, right? And so this is some logic related to B and C. So we need to basically say, okay, how are B and C related to this output? And so to do that, we can use a K-map here. So I'm going to make a K-map then. I'll do it like here, I guess. So let's make a little K-map. And so then the question is, how big should our K-map be? Well, we only really care about these two inputs, B and C, right? And we have 4 possible outputs. So I'm going to make the K-map like this size, and I'm going to say B and C, 0, 1, 0, 1. Okay, so then when B and C are both 0, the output's going to be a 0. When B is 0, C is 1, the output is going to be a 1. And in the other two cases, the output is going to be a 1. So then let me circle these groups here. And we can see that this group is equal to C, and this group is equal to B. Okay, so then this is just equal to B or C. And we can verify this, right? This is literally just the truth table for like an OR gate, right? Because like you're saying, well, here they're both 0, 0. Here this is 1, 1, 1, and that's 1. And then when they're both 1, it's 1. So that's literally just an OR gate. So great. I'm going to take B, and I'm going to take C, and I'm going to feed them into an OR gate. So I'm going to say B and C go into this OR gate, which goes into here. So if A is 0, we're going to say, okay, look at our 0th input line. And our 0th input line is just B or C, so we're going to output B or C. So when A is 0, we output B or C, which is exactly what we want based on this truth table, right? A is 0, we output B or C. Cool. So then the last one is when A is 1. And in this case, I'm not even going to make a K-map, since it's not going to be able to be simplified because we only have one midterm here. And the midterm is just B naught C. Okay, so then I'm going to have an AND gate, and I'm going to feed B into here with a NOT gate, and then I'm going to feed C into here too. So this is B naught C, and then I'm going to just feed this into here. So when A is equal to 1, we're just going to output whatever the value of B naught C is. And you can kind of verify this too just by looking here. B naught C will only be true when, in this case, so again, our truth table matches up with our mux. And so, kind of in general, what we notice is that as the size of the mux decreases, the amount of logic that we're working with on the input lines increases. And so that's like going to be a general pattern that will kind of keep appearing when you work with muxes. And just another important thing to note is that we're doing all of our logic here with the input lines, right? We're not doing any logic with the selector bits. The selector bits are just telling us like which of the input lines we want to essentially activate, right? So what value do we want to input? So if this is 0, 0, we want to output whatever value is on the 0th input line. And yeah, so anyway, hopefully that was a helpful example, just because it's going to be kind of useful to be able to look through these and do it quickly and methodically. And it really just ends up being exactly the same principles that we provide in class, just kind of, taken from a different context. But yeah, so hopefully that helped. Thank you.
Hi everyone, I'm Kat, and today I'll be showing you a faster method of solving mux problems that doesn't require truth tables. Hopefully this can help you solve your homework problems more efficiently and get through the quiz faster. So the first thing I do when I get this problem is I visually examine the logical expression for f. For me, it's just easier to view f as a sum of midterms or a sum of products, and that tells me that f will only ever be equal to 1 if the inputs and the selector bits satisfy these combinations. And when I refer to inputs, I'm talking about inputs C and D, and when I talk about selector bits, I'm referring to selector bits A and B. So the first thing I do is I break up the expression f for f into different cases with respect to the selector bits. And what I mean by that is I know that the selector bits A and B can only be one of 4 different possible combinations. They can be equal to 0, 0, 0, 1, 1, 0, and 1, 1. And this is equal to not A, not B, not A, B, A, not B, and A, B. So now we can kind of relate the logical expression for f with these cases. So the very first minterm in the sum for f is not AB. Off the bat, automatically we're gonna realize that this corresponds to mux input number 1, which is 0, 1. So what this minterm presence tells me in the sum for f, it lets me know that no matter what any of the other input values are, that as soon as A and B is equal to 0, 1, and that mux input is selected, it's going to return a 1. So that tells me that there is a 1 at the mux input corresponding to this case. So that's equal to 1. So now we can look at the next minterm, BD. So this is related to the case where B is equal to 1, A can be anything. But given that we've already taken care of the other case where B is equal to 1, then we know this is going to be in regards to mux input number 3, or AB. So by examining the midterm, I know that I'm going to get a 1 at this input, this mux input, if D is equal to 1, and it'll be a 0 if D is equal to 0. So based off of these cases, I can tell that the value at mux input 3 is just going to be the value of D. So I can draw that over here. So the next minterm is equal to not A, not B, not D. Obviously, this will be in regards to not A, not B, or mux input 0. And I know that I will get a 1 if D is equal to 0, and a 0 if D is equal to 1. So this tells me that the value at the input 0 is just going to be equal to not D. And as you can see from the previous minterm and this current minterm, you can realize this just based off of the fact that D and not D are present in the minterms themselves. So this will be equal to So for our very last minterm, not B, C, not D, this is going to be related to the cases where B is equal to 0 and A can be anything. But given that we've dealt with the other case with B equals to 0, 0, 0, then we know that this is going to be for case for mux input number 2, or the case where it's equal to A, not B. So I know I'll get a 1 at this input if C not D is equal to 1, and a 0 if C not D is equal to 0. So I know basically that at mux input number 2, that this is just equal to the AND of C and not D. And there, your circuit is done. So now we can look at another similar example where basically we just take out one of the min terms. So this means that everything is the same from the previous problem, except for input number 3. So the case where AB is equal to 1, 1. So I know, let me just copy over my work from the previous question. Actually, I can make this neater. All right. So now the last case I need to look at is the case where AB is equal to 1, 1. So just looking at this expression for f, I know that there is going to be a 0 at the input for mux input number 3 or mux input 1, 1. And this is because there is no possible combination of inputs and selector bits when the selector bits are equal to 1, 1. There's no possible combination of inputs that can return a 1 for f. And I know this because there's just no min term regarding to input 1, 1 that just shows up in the expression for f. So that tells me that there's a 0 at this input and my circuit's done. So hopefully that was really helpful. Eventually you can, if you keep practicing, you can get good enough where you just have to look at this expression and you can write your mux inputs from there.